Renyuan from the University of Southern California, where she's assistant professor in the Department of Industrial and Systems Engineering. Before joining USC, she spent 2 years as a Hooke Research Fellow in the Mathematical Institute at the University of Oxford, where she completed her PhD in the IEOR department at UC Berkeley in 2019. Her research interests lie broadly in the span of stochastic analysis, game theory, machine learning, and mathematical finance. And today she'll be speaking to us about reinforcement learning in finance and introduction and survey. Whenever you're ready.
Thanks, David, for the very nice introduction. And I would also like to thank all the organizers for having me speak at this summer camp. Special thanks to David, Seb, Matthew, and Dan. Today I'm going to talk about reinforcement learning in finance. Since this is a tutorial, so I will spend more time on some basic ideas and basic developments, basic tools along this direction. I know Nielsen gave a very nice talk yesterday more on the multi-agent reinforcement learning side and their applications in finance. Today, we are going back to the single agent case, and I will share with you some recent developments along this direction. So this is the plan of my presentation today. First of all, I will give an overview of why we're interested in applying reinforcement learning techniques in financial decision-making problems, and then talk about the basic framework that we apply to these applications. Then I'll talk about some common terminologies used in reinforcement learning, how to evaluate the performance, and how to improve the performance. Then we will move on to talk about two classical reinforcement learning algorithms. So these two methods are like the easiest ones along two different directions. Then we will cover 3 financial decision-making problems. One is optimal execution, the other one is hedging, and the final one is market making. Then we will conclude the tutorial session today. So what is reinforcement learning? Reinforcement learning is a general purpose framework for us to make decisions when we have very limited information about the environment. So an agent, or often called a learner, or a decision maker, operates in an environment, and this environment may be unknown to the agent or partially unknown to the agent. And how the agent interacts with the environment. The agent is allowed to take an action AT at a given time T. So we are talking about a discrete time framework, and this action will have an impact to the future state of the environment. So AT will have an impact to ST+1. ST is the agent's current state. And the success of the actions taken by the agent is measured by a reward signal. So this RT is an instantaneous reward that the agent could collect after taking an action AT. And very often we assume that agent may not know the distribution of this reward signal. So he or she could just get a reward signal RT sampled from some unknown distribution. And this picture tells us how agent interacts with the environment. So agent takes an action, and she or he will observe the reward as well as the next state of the environment. So how should we put this framework into the finance into the finance framework? So this is what we will do. For example, if we have a trader or an investor who operates in a financial market, then this is what we will have. The state represents our current market conditions, current holding positions, some government news, and other information, whatever other information you want to include, and you believe that will help you to improve your decisions. And a popular choice of the action would be the changes in our holding positions of our portfolio. And the reward function, for the reward function, one popular choice is the profit and loss, and we could also modify it to take into consideration the risks we are bearing. And for us, the idea is try to learn from the financial market and try to select actions that could help us to maximize our future reward functions or future P&Ls. So this is how should we put the RL framework into a financial applications. We will use optimal execution as an example to demonstrate how should we model this optimal execution problem as an RL into an RL framework. So optimal execution of large buying or selling positions over a given time period is a very important question faced by all institutions in the financial market. Specifically, when we are trying to do the optimal execution, we need to do a trade-off between two terms. First of all, if we send all our orders at time 0, then we may face a less profitable average execution price because we will introduce a huge market impact by sending this large position to the market. On the other hand, if we trade too slowly and we still have a huge chunk when the time approaches the terminal time, then we need to face the risk of not being able to execute everything. Also, we may also face the risk exposure to unknown market fluctuations because market condition further from the starting point is harder to predict. As a demonstrating example, we will apply model-free RL approach to solve the optimal execution problem. So how should we put the optimal execution problem into this diagram we just showed? So for the state variable S, we could put made price, our current inventory position, and other market conditions as the state variable as we described here, because we want to do, for example, optimal liquidation problem. And the actions we have in mind could be the number of shares we want to liquidate at a given time step. So how, if we want to do a scheduling problem from time 0 to time capital T, then at each given time step T, we can think about how many shares we want to liquidate at that time. And reward function R, this is something we could design by our own. This is also related to the reward design literature in reinforcement learning. For example, if we care about the cash flow we could make, then we can simply use this cash flow. And if we want to see what is the improvement of our trading strategy compared to some benchmark trading strategy, we could use this implementation shortfall. We could also use Sharpe ratio if we want to normalize the profit by the market uncertainty. And there are other choices such as returns or profit and losses. So we have a lot of choices to design our own reward function. And by taking different reward functions, agent will learn different kinds of policies for sure. So this is a small example to demonstrate the framework. And I'll go one step deeper into the classic method on how this problem is solved in the literature. So we could compare the classical method with respect to the new RL method on solving this problem. So in the seminal paper by Green-Crace, which is proposed in 1999, they solved this problem using a control approach. So they consider this problem from time 0 to time capital T, and they use QT to denote their position at time T, and AT is the number of shares they sell at a given time T. Then QT minus AT would be the position at time T minus 1. And I apologize for a typo here. So this ST should be PT. PT is the price of the asset, and it follows a random walk model with the volatility term, uncertain term sigma. And every time the agent sends an selling order, he will moves the price downward. So there would be a permanent price impact modeled in their framework. And this is the cash they could gain by sending an order AT. So we see there's also a temporary price impact that only this trader could observe. So it's the coefficient is this eta here. So the objective function for the trader is to minimize the expected implementation shortfall minus the variance of their position. So that would be the uncertainty they want to consider in their framework. So the nice thing about this framework is that it's simple enough and it captures many ingredients of the optimal execution problem. They could derive explicit solutions, and it's easy to implement because their scheduling solution is only a function of time t, so it's easy to implement. And it is also flexible enough to have various of extensions, and people can also include other ingredients when we focus more on other properties of our decision making. But the drawback of this framework is that it heavily relies on strong model assumptions, such as the dynamics here, because we only use a Brownian motion or a random walk model, but this may not be realistic for many assets. And the solution also depends on how we specify the price impacts. For example, we will only be able, in this framework, we will only be able to solve an explicit solution when we assume linear temporary impact and linear permanent impact. If the market impact doesn't behave like these two functions, then we may suffer from model misspecification. So these assumptions may not hold in practice. So that's the major drawback of classical method. If we won't be able to formulate the control problem accurate enough or close enough to what's happening in reality, then we suffer a lot from model misspecifications. So that's one of the major motivations that we want to consider a model-free approach using this reinforcement learning idea. So the main mathematical framework for most of the reinforcement learning algorithms is through this market decision process. So I'll spend some slides to explain the mathematical notation here. As we know that many financial decision-making problems naturally have a terminal time. So we'll use this finite horizon market decision process as a demonstration, and there is also corresponding framework in infinite time horizon. For example, if we want to maximize if we start from time t and we want to maximize future rewards starting from time t to time capital T, then we want to maximize these a collection of rewards in the expectation sense. So we take the expectation of all our future rewards, and we want to maximize this reward over all possible policies. And this would be the dynamics we are looking at. So the state process as t+1 is sampled from a distribution over the state space, and this transition kernel is a Markovian kernel, so it only depends on SU and AU. So our current state at time U and our action taken at time U. And this action AU is sampled from some policy, and this policy class we considered is also only depending on the current state. Okay, so we are considering a Markovian type of policies. So let me be more specific here. As t is the state of the agent at time t, we can think about that as market conditions and our current position. And at is the action taken by the agent. We sample this action from some policies. This policy pi t depends on the current state, and there are two choices this agent can take. We can either specify a deterministic policy. It means that this policy pi t will be a mapping from the state space to the action space. So once my current state is given, then this policy will give me an action to take. Another popular policy that is considered in the RL literature a lot is this randomized policy. So instead of giving a specific action, this policy, once we fix the state, the policy will give us a distribution over the action space. So the policy will specify a distribution, then we just sample an action according to this distribution. In the classical control literature, we often consider this deterministic policy, which is also called the classical control. And this randomized policy is corresponding to the relaxed control in the control literature. And we will come back to this point on why we want to randomize why we want randomized policy. A high-level takeaway is that when agent has very limited information about the environment, he has uncertainty about his understanding. So he wants to try out different options or different actions to see what would be the reaction from the environment to help him gain more information from the environment. So this randomized policy will encourage exploration of the agent by interacting with the environment. So that's a major takeaway, whereas in the control literature, when we know all the model parameters, we don't need to explore. We can just take the deterministic policy by solving the control problem via HGB equations or Bellman equations. After taking an action at a given state, our agent will then receive an instantaneous reward function R, which depends on XT, ST, and AT, but the agent doesn't know the distribution of this reward. So it's just a sample from some unknown reward distribution. And then the agent will move to the next state according to a Markov transition kernel, but again, this kernel is also unknown to the agent. So the agent could only observe the state without knowing this transition kernel. So this is a typical framework that people use a lot to analyze or design their reinforcement learning frameworks, reinforcement learning algorithms. A key tool that used a lot in designing algorithms or analyzing the problem is this Bellman equation. So if we write the value function like this, so we maximize over all the possible policies, then it gives us the optimal value function VT star, and we can rewrite this optimal value function as the supremum over all action sets on this Q function here. Okay, so we can rewrite our optimal value function, and this Q function is a very basic or fundamental quantity that is used for many RL algorithms. So how this Q function is defined? So this Q function is a function of this pair S and A. So it depends both on the state and both on the action. So it has two parts in its definition. The first part is the expected reward if the agent takes an action A at state S. So this is the expected reward by taking action A. Then the second part is the expected reward of playing optimally afterwards. So after taking action A at state S, the agent will move to the new state S prime according to this transition kernel. And if the agent plays optimally afterwards, then the future reward this agent could collect is this V star T plus 1. Okay, so this would be the future reward collected by our agent if our agent plays optimally thereafter. So this is a combination. So QTSA basically means that what is the expected reward function our agent could collect if she takes an action A at state 0 and then play optimally afterwards. This is also related to the J function in the control literature. And we could derive a Bellman equation for a Q function. So if you look at equation 3, we have Q function on the left-hand side, but on the right-hand side, we have V function. But V function has a relationship with Q function. So we can write a Bellman equation that we only have Q function on both side of the equations, equation 4. So this is the equivalent formulation of equation 3, and that this gives us the Bellman equation of the Q function. So we have Q function on both sides of our equation, and we also have a terminal condition. So QT star, Q star at capital time T is just the expected reward of the expectation of the terminal reward. So this equation 4 and 5 are the fundamental pieces or very important pieces, building blocks for many reinforcement learning algorithms. And these two equations are previously used a lot in the control literature if we want to solve for optimal controls or we want to design numerical methods to approximate the optimal value function. Okay, so in the classical control literature, we will assume the distribution of R and the transition kernels to be given, so we could solve VT star or pi star by iteratively updates to this equation 3. So if we could solve this analytically or numerically, then this equation 3 will give us the solution. On the other hand, if we don't have any prior knowledge about the model, and we could construct solutions to equation 4 or equation 3 by using samples. So what do I mean by samples is that we interact with the environment from time t to time 0 to time capital T minus 1. Then we will collect some samples with tuple like this. So each tuple is ST, AT, ST plus 1, RT plus 1. So this is by doing interaction with the environment for one time, we will get a tuple. And then if we run this experiment for multiple episodes, so I is the number of episodes, how many times we repeatedly playing with the environment, we have a lot of samples, then we could use these samples to construct a solution to equation 4. So that's basically what most of the RL algorithms are trying to do. So we use whatever we could collect from the environment to construct approximated solutions to this Bellman equation. So that's the key idea of how should we connect reinforcement learning algorithms and the classic control literature. Okay, so they are closely related. They just solve this equation by using different ingredients. So there are a few main components of each RL algorithm. So an RL agent may construct her learning policy or her algorithm by using one or more of the following ingredients, but these are 3 major ingredients that could classify almost all existing algorithms. So the first component is a representation of a value function. So we keep track of the current value function of a given policy. So that would be our VTS pi function. And then we could also use some memory to represent our current policy. So we keep track of what is the current policy that we are using. So we maintain an evaluation or maintain a memory on the policy pi. And if in addition to learning the policy and value function, if we still want to know something about the environment, for example, we want to construct an approximation to the true transition kernel P, or the distribution of RT, we can also maintain an estimation of the environment. But the third ingredient is very computationally inefficient. But I know that for some applications, we do want to have a better understanding of the environment. So people also include this ingredient for some algorithms as well. Okay. And all the components we mentioned above should be or can be constructed based on observations. So again, we use all these observations that we collect by interacting with the environment to construct all these 3 ingredients. And if we have a very nice way in the sense that we have theoretical guarantees, statistical guarantees for the representations we construct, then the algorithm could converge and we could say something more from a theoretical perspective on how good our learned policy is and how good our learned value function is. Now, David, should I take questions in the middle or we have discussions in the end? I'll pause here to see how should we do that?
It's up to you.
Okay. then I'll pause here for a few seconds to see if there are any questions before we move on to the next module.
I'm not seeing any hands. So,
Okay, sounds
go ahead.
good. I'll move forward. So this is a classification of RL algorithms. As we mentioned, there are three major components. The first one is the model, the second one is the policy, and the last one is the value function. If we want to maintain an approximation to the model, then this is called the model-based method. And if we don't want to maintain an estimation of the model, this would be model-free method. Among the model-free methods, if we maintain an estimation of the policy, then this is called policy-based method. Examples include proximal policy optimization, reinforce, and trust region method. And if, on the other hand, we don't parameterize our policies directly, instead we want to learn the optimal value function, then this is called a value-based method. Examples include the classic Q-learning method and its variants. And if we want to combine both and maintain an estimation for both the value function and the policy, then there are also methods along this direction. The most famous one is the actor critique method and its variants. And another part I want to introduce is this evaluation criteria. When we design an algorithm, how should we evaluate the algorithm? So there are mainly two perspectives, and the evaluation is performed in terms of the number of episodes. So if we run the algorithm from time 0 to time capital T minus 1, and we collect a lot of tuples, this is defined as running this experiment by one episode. And if we run this experiment repeatedly for many episodes, we want to know how good our learned policy or value function is with respect to the number of episodes we've run. Okay. So the first notion is called the asymptotic convergence. If we denote Vn as the output of the value function at the nth episode, and we measure the difference between our estimated value function and the optimal value function, if the difference converges to 0 when the number of episodes goes to infinity, then we call this asymptotic convergence. So eventually, if we run the algorithm for many or enough episodes, then we do get a good estimation in the end. So this is asymptotic convergence. And if we want to quantify how fast our algorithm converges to the optimal one, then we have this notion called sample complexity. Basically, we specify an error that we could tolerate. So we specify this epsilon, and the number of episodes we need to run the algorithm in order to reach this accuracy is called the number of the sample complexity. So this number n would be the number of episodes we need to run in order to reach this epsilon. So this gives us a finite sample analysis. This is called a sample complexity. And we use the notion V to denote all these criteria, but we could also define them through the Q function, or if we do policy-based method, we could also use policies to construct these evaluation criteria. Okay. I see a question in the chat. Okay, guess it's not for me. I'll continue. After talking about these methodologies, I will introduce two classical methods in the RL literature, very basic ones. For the value-based method, we will talk about Q-learning algorithm and see how to use the Bellman equation we just introduced to construct a Q-learning method. And another one, reinforce, is one of the classical methods under the policy-based method. Let's start with this Q-learning algorithm first. And for simplicity, we will focus on the scenario where we have finite state and finite action space. So recall that the optimal Q function, Q star, satisfies this Bellman equation. But as we know, if we don't know the distribution, we don't know the transition kernel here, we won't be able to calculate this expectation. So what should we do in this case? The idea is simple. We just use the samples we could observe to construct a stochastic approximation to this Bellman equation here. When we can't solve these we can't calculate these expectations, we use samples to approximate these expectations. Okay, so what should we do in the nth episode? This is the step that we would use to update our estimation of the Q function. So it's a linear combination of the old estimation and the new estimation. And we use this learning rate beta to do the trade-off. If we are more aggressive, then we put a bigger beta. If we are conservative, then we just put a small beta. So we put more weight on the old estimation. And we can see that in this new estimation, this new estimation term is just a one sample estimation to the right-hand side of the Bellman equation. So we use one sample to estimate this expectation here, and we also use one sample to estimate this expectation here. So it's really a stochastic approximation. So this is a simplest version that we only use one sample to estimate the right-hand side. If you want more sophisticated model saying that I want to have an estimator with good statistical guarantee, low variance, then you can play around with the updating rule and maybe include more samples here for your new estimation. So, but the key idea is that we use samples to construct stochastic approximation scheme to the Bellman equation. So that's the key idea for Q learning algorithm. And as we discussed, beta n is the trade-off. Beta n is the learning rate, and it's used to do the trade-off between the current estimation and the new estimation. So there are, you may have several questions on when will this method work? The first question is, how should we do samples? Because here we know that for a given sample, we could update our Q function like this, but in practice, what's the way of collecting these samples? Okay, this is a very famous result in the 90s. So if we denote n as the nth time to visit a given state and action pair, our collected data should satisfy this formula. So basically, if we count the learning rate for all the times that we visit a given state and action pair, the summation should be infinity. That means we need to visit each state and action pair infinite number of times to make sure that our stochastic approximation works. So it's accurate enough. So so this reflects in the first condition here. The second condition is that for sure, we want to visit each state action pair infinitely many times, but we don't want to do it in a very inefficient way. We still want to do it efficiently in the sense that the summation of beta square should be bounded. Okay, so we don't want to waste samples if we already know well enough about the Q function at a given state and action pair, then we can slowly decrease the times that we visit it. So the summation of beta square should be bounded if these two conditions in equation 6 are satisfied. Then asymptotically, we know that our Q learning updating rule is converging to the optimal one. Okay, so as long as equation 6 is satisfied, then our stochastic approximation scheme will converge to this Q star function eventually. And this equation 6 holds under various exploration methods because we want to make sure that the visitation requirement is satisfied. And on the next page, I will talk about these two exploration methods as well. And another question you may have is that why we want to learn Q function? If we have a good understanding of a Q function, how should we use it? And the answer is that there is a natural policy that is embedded behind the Q function. So if we have a Q function, then what we should do is that we should simply take the action that could maximize the Q function for a given state, because by doing that, we could recover the optimal value function. Okay? So the Q function suggests a policy. We just take the optimal action at a given state, and that should be the optimal policy for our problem. Okay. And and this is what we should do. And now I move on to these two exploration methods we just introduced. So there are two popular exploration methods that people explore a lot in practice. The first one is called epsilon greedy method. For example, if Qt is our current estimation of the Q function, then epsilon greedy suggests that with a very high probability, we take the action that could maximize our current Q function. And with a very small probability, we just randomly sample an action from the action space to do exploration to see that to see whether we should correct our current belief of the Q function or not. Okay. Another popular method is called the Boltzmann policy, which is from the physics. Boltzmann exploration, and we have this exponential function, and we have a temperature parameter. Okay, so we sample an action according to this probability. Okay, so according to its Q value function, and we could see that if we let lambda goes to epsilon, then this recovers. If we let lambda goes to epsilon, then this is uniform distribution. We just randomly sample according to the action. However, if we let lambda goes to infinity, that recovers this greedy policy. Okay, so then you can see that by having a non-zero number, then this has a trade-off between the greedy policy and a uniform sampling from the action space. So this also gives us a way to do exploration and to see whether we should correct our current belief or not. Okay. And when we have very limited information about the environment, this exploration versus exploitation trade-off is very crucial for the design of our algorithms, especially from the perspective of efficiency, because we know that exploration could provide us with opportunities to improve from current suboptimal solution. But if we explore too much, then we may waste a lot of samples, and it may have a negative impact on how fast our algorithm could converge to the optimal one. But on the other hand, if we do pure exploitation only based on our current estimation, then very likely we will converge to a suboptimal solution, which is very far away from the global one. So how to efficiently do the trade-off between exploration and exploitation, and at a given training stage, how much effort we should spend in exploration is a very important subject, and there are a lot of ongoing works and a lot of recent results on trying to balance these two perspectives from a theoretical point of view. Okay, and if we come back to the optimal execution example we introduced at the very beginning, then this is how a Q-learning method should be implemented in practice. Okay, so we assume that we could observe the real market price P, and we know that our current inventory is I. Then we take an action based on our current estimation of the Q function. For example, at the current time t, I take the action that could maximize my current Q function. Then we send this order to the market. After we send our order to the market at time t, we will receive these two quantities from the environment. So we will know the execution price of our order, and we will also be able to observe the price of the asset for the next timestamp. Okay, for example, the made price of the new period. And by interacting with the market for this one timestamp, we will collect a tuple from the market: the current state, our action, the reward, which is the executed price, and then the next state. So we will collect one sample from the market. one comment I really want to make is that in practice, it's impossible to train the algorithm in real market, because when the algorithm is not intelligent, we may lose a lot of money by sending orders using that market. So realistically, most of the reinforcement learning algorithms are trained with a market simulator, and the market simulator is based on historical data. And there are also some theoretical research challenges on how to construct a realistic market simulator. I think once we have a good understanding of that, then we will be able to see more applications of reinforcement learning in finance. Without a good market simulator, I do see some limitations of making it happen. So after discussing about what value-based method is, then I'll also touch upon a bit on the value-based method to see how should we improve directly for our policies instead of without keep track of the value functions. So very often when we are thinking about a policy, we would like to parameterize the policy by either using neural networks or linear functions as well as other functions. So we parameterize our policy, which is a distribution over the action space by this parameter theta here. You could think about this theta as some parameterized functions or your favorite neural networks. Okay? And then we could just use j theta to denote the value denote the expected value function under the choice under the condition that we take policy pi theta. Okay? So for policy-based method, we often work with this aggregated value function. So this basically implies that we take initial state according to some distribution, okay, some stationary distribution. We work with this j theta instead of vs here. So we aggregate all the initial states and we work with this value. We work with this particular value function that is a function of theta. So theta is the parameter for the policy, and we see how should we improve improve our current estimation of theta. So what is the best theta? Okay. So many of the policy-based methods are constructed based on this theorem, which is called the policy gradient theorem. It gives us a very nice expression to calculate the gradient, because naturally, if we want to find a theta to maximize, this j function, then one natural idea is to take gradient. And if we see here, if we take gradient here, and if we don't have a good expression for that, then this is very difficult because theta is basically everywhere in this formula here. And what this policy gradient theorem tells us is that indeed we could find a very simple formula for the gradient, and we could use this expression here to construct or to approximate the gradient when we won't be able to calculate this gradient precisely. Okay, so this theorem basically tells us that the gradient of the j function with respect to theta can be written as an expectation here. Within this expectation, it's a summation over all actions of a product here, and the first term is the gradient of the log policy term here, and the second gradient is a Q function associated with this policy pi theta. Okay, so this expression is easier to work with because remember, in the value function here, it's a summation of t terms. Okay, if we want to solve the value function for a given time t, or if we want to solve an infinite time horizon problem, then this v function involves a summation of many terms, whereas in this policy gradient theorem, it's only a summation over the action space. There will be no summation with respect to time t, and that helps a lot in terms of designing algorithms. Okay, so we have many policy-based methods, and they all try to approximate this term inside the expectation, or they try to approximate this expectation as a whole, but they use different ideas to do the approximation. But essentially, the key idea is to try to approximate this gradient so that you have a more or less correct direction to do the descent and try to improve your policy theta. Okay, so that's the key idea for almost all the policy gradient-based methods. Try to approximate this expectation here and then find a direction to do the descent step. And reinforce is one of the classic method to do the approximation here, And what the algorithm says is that we run the policy for long enough and we collect some rewards here. And this GT is the sum of the expected reward starting from time t+1 to a given capital time t. And what we did is that this GT actually approximates this Q function here. And our policy parameter is updated using this equation 10. So you see that the difference of equation 10 and this equation 9 is that we use this GT function to approximate the Q function, and we also have the gradient of the log policy here in front. Okay, so we use this GT function to approximate Q, and we use this expression to approximate this expectation, and that helps us to find a direction to update our parameter theta. So we go from theta n to theta n+1 by descending our estimation towards this direction. Okay, so that's a key idea. So Monte Carlo method, so reinforce is a Monte Carlo based method because we need to collect some future rewards in order to approximate this Q function here. And there are other ways of doing that, but almost all the policy-based methods are trying to construct some approximations here. So if you see other policy-based methods, you will be able to understand what does where do those techniques come from. So it's all about approximating the gradient term with respect to the parameter here. So do we have any theoretical guarantees for reinforce? Because this is a popular algorithm that people use for decades. And this algorithm exists for a very long time, but the global convergence is only established very recently. So last year in this paper from a group in Stanford, they provide a sublinear high probability regret bound. So regret is another notion to quantify how good an algorithm is, but we didn't have time to cover that previously. One comment I want to make is that there is a translation between sample complexity, which is the notion we introduced, and the regret. So there's a one-to-one correspondence. You can translate these two results. And another question is, do we have other policy-based methods? The answer is yes. And a few examples are listed here. Trust region policy optimization, they add KL divergence in their formulas to stabilize the training process. And there are like proximal policy gradient methods, neural policy gradient method when you use neural networks to approximate the policy. So there are other developments as well, but the main takeaway is that we want to approximate this gradient of J with respect to theta. So that's the key takeaway for policy-based methods. Okay. And before talking about financial applications, I do want to share some of my personal views on when should we use value-based method and when should we use a policy-based method. So the main advantage that people like to use policy-based method is that it directly parameterize the policy. So we have a better understanding of what good policy looks like. And this is the most thing we care about. We want a good policy that could work for a given environment. And And when people perform empirical analysis, when they compare value-based method versus policy-based method, most of the results, they indicate that policy-based methods tend to be more stable and less prone to failures. So that's why people like to use policy-based method, because it's more stable. And value-based methods, such as the Q-learning methods we introduced in the very beginning, it is less stable and it may suffer from poor convergence. And that's why we see a lot of variants or modifications of the classic Q-learning method, that they are trying to solve these issues of instability and poor convergence result. Okay, but on the other hand, Q-learning method is also very popular in practice because it has its own advantages. It is an off-policy method. We don't need to collect samples based on our current estimation of the policy. If we have historical data collected by other policies, we could still utilize those data to estimate our Q function. In that sense, if we can't run the algorithm in practice, but we have historical data, then Q-learning methods gives us a good initial starting point to construct something, because it works. It also works with data collected by other behavioral policy or some old policies. So that's the benefit of Q-learning method. It can help us to utilize or exploit data from other experts or other data sources. So that's the benefit of value-based methods, or particularly Q-learning methods. I think I see a few comments in chat. I'll see if there are any questions before we move on and talk about financial applications. We have one question. Can we train the algorithm with the real market data, but without using real money? You can send paper money saying that I want to see if I follow the current market condition and I have a paper account, I see how much money I could gain. That may work, but the only issue is that if you don't use real money, you don't send a real order to the market, you won't be able to see the market impact of your data. So you won't be able to see how your action impacts the future, like limit order book dynamics. So that's a drawback of mimicking the market, constructing a paper account without sending real money. So the market impact part won't be captured. But if you don't care about your market impact, then this may work. Okay. Okay, so now we move on to talk about a few financial decision-making problems that we have quite some results, not me, but other researchers have quite some nice results on applying RL algorithms to these applications. Okay, so we use this optimal execution as a demonstrating example, but I do have a few additional remarks to give you some comprehensive view on how people use RL for this application. And so this is a summary of our recent survey paper on this topic. If you're in, we covered more applications, but due to time limit, we will only be able to discuss these three applications in my presentation today. But if you're interested, feel free to check out our survey paper, Recent Advances in Reinforcement Learning in Finance. So in this paper, for optimal execution, we summarized a few papers. So the most popular RL algorithms that people use in optimal execution are Q-learning algorithms or double deep Q-learning method. So double deep Q-learning method is a variation or a modification of the classic Q-learning method we just introduced, but they use neural network and they use two neural networks. The key idea is to stabilize the training process, and we will have one page slide to talk about this method. There are 7 papers using Q-learning based method to do optimal execution. And on the other hand, policy-based methods are also quite popular, including deep policy gradient method, A to C method, proximal policy optimization, and deep deterministic policy gradient method. So we have like 6 papers. When we wrote, up to the time we wrote this survey paper, there are 6 papers discussing how to use policy gradient, policy-based method to solve optimal execution. And when they are trying to compare the performance of their algorithms with the benchmark strategies used in these studies include the Almgren-Kris closed form solution. We covered that earlier, and the VWAP and TWAP strategies. So those are some simple strategies that we are all aware of. And another benchmark strategy used in these papers is the submit and leave policy. Basically, we submit all our orders at time 0, and then they compare the improvement with respect to this simple strategy. And the performance measures in these papers include the profit and loss, implementation shortfall, and Sharpe ratios. So these are the performance measures we also covered at the very beginning. So this is a summary of the current status of reinforcement learning in optimal execution. And since this double deep Q network is very popular for financial applications, and I'll give some high-level idea on what this algorithm is and why people prefer this method. So in this double deep Q learning problem, we have 2 value functions that are learned by assigning experiences randomly to update one of the 2 value functions. So that's why we have a 2 weight theta and eta. So in each update, one set of these neural network weights is used to determine the policy that we want to use. And another one is used to determine its value function. Okay. So one Q function is used to maintain the estimation of the Q function, and another weight is used to determine what is the action we should take. By separating these 2 goals, we have empirical observations to show that this is more stable than using only one neural network theta to parameterize the Q function. So that's a major takeaway of why we want to introduce 2 networks. So it separates the way of using Q function, and then it stabilizes the training. Otherwise, we need to use a single Q function at several places, and that may introduce instability, especially when our estimation of the Q function is not accurate enough. So I won't go into the details, but the key takeaway is to introduce another neural network to stabilize the training process. And if you're interested, you can take a look at this paper, Deep Reinforcement Learning with Double Q Learning. Okay, so that's a quick introduction, and now I will introduce this paper by Ning Lin and Jamango. So this is a very well-known paper in this direction, and I like this paper a lot. They applied this double deep Q learning algorithm. So it's the algorithm I introduced very quickly for optimal execution. The state variables they consider is the price, the volatility, and they also mentioned that it's possible to include other limit order books features as well. So it's a flexible framework. And the action they take is the quantity to trade in each time interval. So that's a standard setup. And the reward they consider for each time period is the increment of the profit and loss minus a penalty on a large trade. Because when we send a large trade, that introduces a market impact. So they have a penalty on that. And they also define a Q function based on volatility levels. And one observation they have is that for the same level of inventory at each time t, the optimal strategy tends to send more shares when we move from the low price regime to high price regime. So the trend algorithm is very sensitive to the price level that we are currently have. If the price is smaller, then we send more buy orders. And if the price is higher, then we send fewer buy orders. So that's a sanity check to show that this algorithm actually works well in practice because it's sensitive to the price ranges that we could possibly have during a long time interval. And they also performed their algorithms with real world data. So they tested on Apple and Amazon stock, and they calculate the probability that their increment of P&L is positive. So they are earning monies. So the probability of earning money is around 70% for Apple and 50% for Amazon. And they also showed that their algorithms beat benchmark strategies for large proportion of the time. Okay. And the next topic I want to introduce is this option pricing and hedging. And very similar to what we did in the optimal execution part, I'll first talk about how this problem is solved using classical method, and then I will talk about the limitations of classic method before moving on to talk about how people do this using RL method. Okay. So hedging strategies are used by all kinds of investors to reduce their exposure to risk. When this can be done properly, hedging strategy could help us to reduce the uncertainty in our positions and limit the losses we could encounter without sacrificing too much about the rate of returns. So that's a key level idea. I know many of you already have background in quantitative finance and mathematical finance. I'll skip the introduction here. Okay. So if we take a European option as an example, this is how we do the pricing part of the European option. If we denote ST as the stock price, we can think about this as the made price of the name order book. Then there is a European call option with a strike price K, and the exercise time is capital T. At capital time T, the value of this option is denoted as this. So it's the maximum of the price, the difference between the terminal price and the strike price versus 0. So if this exceeds 0, we have a positive number because we can execute that to gain money. Otherwise, the value is 0. The question we want to ask is that what is the value or what is the price of this call option at any given time small t before the maturity time? Okay, and the answer is that if we assume that ST follows a geometric Brownian motion, then the Black-Scholes-Merton formula framework tells us that we can get a expression for the value if ST is the current price at time t. So we have an expression here, and all these functions can be called all these functions are tractable through the standard normal cumulative distribution function. And I have a small picture here to show you what is the risk contained in the European option and how should we try our best to minimize our risk exposure. So these are some simulated paths starting from a price 100, and we look at different volatilities, different levels of volatilities maintained in the price dynamics. When we take sigma equals to 0.5, so these are some trajectories. We see it fluctuates between 70 and almost 140. However, if we increase this level of volatility to 1.5, then you see a lot of big fluctuations in our sampled trajectories. So the price price dynamics range from close to 0 to 300. So we have a lot of fluctuations, bigger fluctuations compared to the price trajectories when we have a small volatility. So we can see that paths on the right-hand side are more volatile so it contains more risk. We don't want to have so much uncertainty if we trade based on these underlying assets. And what Black-Scholes and Merton model tells us is that by shorting the position for delta T unit at time T with this quantity here, so this delta T is the derivative of phi respect to S, then the risk contained on the call option could be eliminated. So we pair our call option with this hedging strategy. So we short delta T units at time T, and this could help us to eliminate the risk without sacrificing too much on the return. So the benefits of this method is that the formulas are easy to implement to some high-level extent because we know how to calculate this derivative. So we have a formula to implement it. So it is easy to implement to some extent, and it works well for markets that are nearly frictionless. And it works well for simple settings, such as we only have one option in our portfolio. But the drawback of this framework is that the classical Black-Scholes model gives pricing and hedging strategies under very strong model assumptions. For example, this works for geometric Brownian motion, and it may not hold in practice. And also another major issue is that when transaction costs and options premiums are considered in the framework, then usually there's no closed form solution to solve the problem. So it will be harder to implement along this direction. And when we have multiple assets in higher dimensions, there's also no closed form solution for us to implement the hedging strategy. And especially when we need to include assets from different asset classes, it's different to model the relationships among these assets from different classes. So there's a lot of limitation in terms of how to model it, how to model the relationship between different assets, and how to quantify the optimal hedging strategy. Okay. And also sometimes it may be difficult to rebalance on a very high frequency. And we know that this is defined for a price process. But if we want to send our orders to limit order books, there would be implementation errors in practice because of the market microstructure. Because, for example, the tick size, the difference between the best bid, best ask level. So those features will introduce errors when we implement this method. So those are some limitations of the classic methods, and that's why we see many nice recent papers on trying to derive hedging strategies by using machine learning methods. Okay, so in this survey paper, we summarized a few very nice papers on learning hedging strategies directly. And the RL method used in these papers include Q-learning, deep Q-learning method, as well as two policy-based method. One is the proximal policy optimization method. The other one is DDPG. And for these methods, in this paper, the state variables they considered often include the asset price, the current positions, option strikes, and the time remaining to expiry, the expiry time. So these are the popular state variables in these papers. And the control variables is often said to be the change in their holding positions or hedging positions. And I think for this particular application, people care a lot about risk. So they often adjust their reward functions or value functions with this risk measures, for example, value at risk, expected shortfall, or variance to minimize risk, to make sure our value function is more sensitive to risk. And I will briefly talk about this paper. It's a very nice paper. It's a joint work between the JP Morgan group and ETH. Okay. The goal of their paper is to learn the optimal trading strategy for hedging instruments to mitigate the risk of holding a portfolio of illiquid contingent claims. So I'll skip the definition here because I know many of you know what is contingent claims. It's a very general financial agreement and in the over-the-counter market. So over-the-counter market has a lot of illiquid assets. It's quite challenging to model them from a stochastic control approach. So, so this is the idea of what they want to do. And the state variables considered in this particular paper are the current and past prices and the cost estimations, news, and anything else that they think are necessary for them to determine the risk management strategies. So you see the one benefit of using RL algorithm is that it's very flexible. We can include whatever features we want into the state space as long as we think that they are relevant for us to improve the strategy, like microscope news, public announcements. For all those things, we could include them in our framework, in our model, to see what are the impacts of these news to the decision that we want to improve. And the actions they consider, and sometimes if you think the current price is not good enough for us to determine the action, we could also include past prices into the state dynamics to train the model. Okay. And the action considered in this paper is how much to trade in each holding hedging instrument subject to certain constraints. So they have constraints in their action space. So it's a constrained decision-making problem. And they adjusted their value functions with this expected shortfall. So they care about the risk. So this is the cost or the negative reward function considered in their paper. So what they could show is that by designing this framework, the algorithm works well and it beats benchmark strategies by using classic method for many situations. And another nice observation or takeaway they have is that the neural network architecture actually plays a role here. So they compared the performance between a very simple neural network and a recurrent neural network, which is very good at extracting information from time series. What they could show is that the recurrent neural network has a much better performance compared to simple networks. And simpler non-recurrent neural network yields a much higher, so less optimal minimum price. So that means if you want to use deep learning type of method, try to explore a few different architectures and see which one gives you a better performance. Because in this example, they showed that the architecture does matter. Sometimes in practice, from a practical perspective, we do need to try several different architectures before we conclude with the policy that we are happy with. I think I still have about 15 minutes. I'll talk about the final application, which is the market making in a limit order book. So we move back to the equity market. A market maker in a financial instrument is an individual trader or an institution that provides liquidity to the market by keep placing buy orders and sell limit buy orders and limit sell orders in the limit order book. For example, this is a realization or a screenshot of a limit order book. By the way, this picture is from Sepp's book, Sepp's and Navarro's book. So we see that we have a lot of limit orders at higher prices. So these are limit sell orders because people want to sell orders at a higher price and they want to buy orders at a lower price. So we see a lot of clustered queues to sell orders at different prices. Then there would be a gap between this cluster, this blue cluster, and this red cluster. Okay, and at lower price levels, there would be a lot of limit buy orders who want to buy a given asset at a lower price. And we see there's a difference here. So the best price on the sell order is called the best ask price, and the best price on the buy side is called the best bid price. The difference between the best ask price and the best bid price is called the spread. For most of the liquid asset, the spread is almost equals to the tick size for most of the time. Okay. So what market maker is trying to do is that they want to put limit sell orders at the best ask price, and they want to put limit buy orders at the best ask side. So they post orders on both sides. If their orders could be executed, then they sell at a high price, buy at a low price, then they could earn the spread. So the goal for market maker is to earn this spread. They don't have any intention to do the optimal execution as we introduced at the very beginning, and they are not interested in keeping any inventory. What they want to do is they want to keep a low inventory on both sides of the market and try to make the spread. Sometimes they may go deeper into the book, saying that I put a sell order here on the second best level, and I put a buy order on the second best level. Then they could earn more money by making a successful round trip, because they could earn a few more ticks by doing that trade. So that's a description of what market maker is trying to do in the limit order book. Okay. So the classic control approach models the mid price of the limit order book by a Brownian motion, and this QT is the inventory of the market maker. So this is a signed inventory, because this is the inventory on the buy side, and this is the inventory on the ask side. We have a sign here, so this is a signed inventory. Okay, and NB and NQ are the number of shares bought and sold respectively, and by making those trades, this would be the cash of our market maker at time t. You see that if this is successful, then we earn half of the spread. So this is the ask spread, and this is the bid spread. If they post at different levels, then this half spread may be different for different orders. But this is the cash that made by the market maker, and the market maker chooses the spread to maximize the utility function. So they can choose one tick, they can choose a few steps, a few ticks away from each other, and the goal is to minimize, to maximize the total revenues they could make, and they also want to have a penalty on the terminal inventory, because market makers don't want to carry the risk of overnight inventory. So they want to have a zero inventory when the market closes. So this is the classic control framework, which you can find in this very nice paper dealing with the inventory risk solution to the market making problem. It's a very nice paper. But we can see that there are a few limitations by using the classic control literature, although this is a very nice paper. First of all, this may not be the mid price dynamics. And second of all, when we calculate this, so when we formulate this NA and NB, so how many of shares that could be bought and sold respectively are modeled by some Pearson processes with a given arrival rate, and that assumption may not hold in practice when we look into the limit order book dynamics. So that may be another limitation here. And that's why we want to move to the RL regime. So under the RL framework, most of the developments are centered around value-based methods such as Q-learning algorithm, or the online version of the Q-learning method, which is the SARSA algorithm. And for this market making problem, the state variables considered in this paper are often composed of bid and ask price, because for this application, we need to go deep into the market microstructure. We need to extract useful information from the limit order book dynamics. That's why they want to consider the bid price and ask price. they also have the order flow imbalance, because that's a good indicator to predict the next step of the limit order book dynamics. So they have the order book imbalance, have the volatility considers current holding positions because we want to have low inventory, and also we can include some sophisticated market indexes constructed by using features from the limit order book. And the control variables are typically set to be the spread, because we want to make round trip, then you need to send orders on both sides. And if we send the same number of shares on both sides, then we can use the spread to formulate a pair of limit buy and limit sell orders. And the examples of the reward function are is just the standard part plus an inventory cost, because we use the standard measures to measure the performance, but for this particular application, inventory cost is very important. So we need to penalize the inventory at the end. We don't want to hold the inventory overnight. So in this paper, market making via reinforcement learning from a group, I think it's a joint work with a group in Liverpool and JP Morgan. The goal in this paper is try to make profits by buying low and selling high and keep low inventory at the same time. So it's very similar to what we just described. And in this particular paper, the states they considered include the market spread. So the spread between the best bid price and the best ask price, the made price movements, and the book imbalance, signed volume, volatility, and relative strength index. So they consider all these state variables. When we go into the market microstructure, it makes sense that we need to include more data, because we care about what happens in the next second or the next few milliseconds. And the actions they considered in that paper has a size of 9. So they consider 9 actions. So they send a pair of limit buy and limit sell orders at different price levels. So these are the levels of combinations they consider. So they are total 9 actions. And the reward they considered is the standard profit and loss plus a penalty on the inventory. And what they could show is that they compare the out of sample performance of their proposed method with other benchmark methods, and they could show that for almost all situations they could improve their strategy improves from almost all benchmark strategies. So you see there's indeed a lot of room for reinforcement learning algorithms to improve our decision-making problems in finance, our decisions in financial markets. And I think I'm a few minutes ahead of time. I'll conclude my presentation today. So through my presentation, we discussed about a few terminologies used a lot in the RL literature, and we introduced 2 classic methods in reinforcement learning, and we talk about their applications in finance. And one takeaway I want to emphasize is that domain knowledge is very important for us to apply RL method in finance, because by comparing the 3 applications we introduced, you already have a flavor that for different problems, we care about different aspects, and we need to adjust the framework accordingly. We have inventory risk, we have other risk, and we have other things. We need to we take different kind of actions. We need to modify the framework according to the problem itself. So domain knowledge is very important. It can help us to have a better understanding about the environment. And if we could design problem-dependent state space and action space, it helps a lot to improve the sample efficiency. I think from a control perspective, we sometimes want our framework to be as general as possible. But I think for the designing of a specific algorithm, we want it to be as specific as possible, because if you include all the ingredients that you could find from that problem into your algorithm, it's often more efficient because you utilized all those information to help you design a more efficient algorithm. Another takeaway I want to share with everyone is that we need to have a combined view on reinforcement learning algorithm. It's still in its early stages, and we haven't seen many applications in real world training. So it has its benefits and it also has its drawbacks. We need to have a combined view on this RL method in financial applications, and I do hope that the community keeps evolving, and we will be able to see more and more good results along this direction. So a few benefits of RL method are that they don't rely on any model assumptions. We don't need to make assumption on the state dynamics and other things. So that's very flexible. And we can see that it's easy to extend to multi-asset scenarios because we don't need to model the relationship among different assets, and that's difficult for many many stochastic control approaches. And the drawback of RL method is that many RL methods need a lot of sample to converge. If we don't have so many samples for us to train the algorithm, then it has a lot of limitations. And in practice, institutions cannot afford trying stupid strategies on the real market. They can't afford the losses. So when you put an algorithm into the market, you need to be sure that it doesn't introduce a lot of losses. Okay. And then another challenge is that financial market is often non-stationary, and the information to noise ratio is very low. That's a key difference compared to other environments that RL has a lot of successes. So there are still a lot of challenges and open questions at this moment on how to apply this technique to financial decision-making problems. I'll stop my presentation here. Thanks everyone for coming to my presentation.
Okay, thank you very much. Are there any questions?
Hey, so you talked